Hello everyone, this video is going to introduce Explainable Artificial Intelligence. No matter you are a kid, a banker, an artist, or a farmer, you more or less heard about this term, artificial intelligence. It tries to model the most significant intellectual functions of the human brain and exists in almost every corner in our everyday life, such as Siri, Face ID, Amazon customer service online chat, personal financial assistant, all kinds of social media, autonomous vehicles, or our handsome human-like NPCs in our favorite games. They make our life easy and fun. However, AI also makes wrong decisions that cost money, even cost human lives. In 2018, Ellen Herzberg died at her 49 after she was hit by a Volvo SUV, which Uber had been using to test its self-driving technology. The driver was in the driver's seat and was traveling at about 40 miles per hour in autonomous mode at night. The responsibility of such a tragedy is not only the drivers, but also the self-driving AI systems. This type of accidents continuously happen and destroy our trust in AI technology. Many companies will or already launched their autonomous vehicles on the road, claiming that they will deliver a big boost to road safety. AutoX has rolled out fully driverless robot taxis on the road of downtown Shenzhen, China in 2021. Motional announced plans to start a commercial driverless ride-hailing program with Lyft in Las Vegas by 2023. Uber, after the fatal accident, still had their self-driving cars on the roads in public testing in Pittsburgh, Pennsylvania, San Francisco, and California. To avoid such fatal costs during the development of AI, the social, ethical, and legal pressure calls for new AI techniques that are capable of making decisions explainable and understandable. It is a must for an AI-involved system to provide a human understandable explanation that expresses the rationale of the machine in order to win back our trust. This is the rise of explainable AI, XAI. Actually, the problem of explainability in AI has already existed since the mid-1970s, when researchers studied explanation for expert systems. Now it gains more attention with the unstoppable evolution in machine learning across industries and its crucial impact in critical decision-making process. The majority of machine learning models work as black boxes. Given an input, a black box returns the result of a decision. No detailed information about the chain of reasoning can be provided to illustrate why certain decisions, recommendations, predictions, or actions are made. So to explain a machine learning technique, an interpretable model is required to approximate the black box model as much as possible. There are three methods to achieve the goal. The first is global method, which is developed to understand the entire model behavior, the whole logic of a model, and follows the entire reasoning leading to all the different possible outcomes. For example, a global model interpretation via recursive partitioning builds a global interpretation tree for a wide range of machine learning models based on their local explanations. To be more specific, let's use a machine learning model to predict which type of room it is in the pictures. The first column is the raw picture. The second column shows that semantic categories that found by the semantic segmentation algorithm. Column 3 shows actual semantic segmentation, which contains several superpixels for each image. Column 4 presents the important semantic superpixels with highest contribution scores that are highlighted green for corresponding ground truth category scores. Take the second picture as an example. A decision tree is created for determining a living room image, where sofa, window pane, and fireplace are important factors. By following the tree according to the superpixels, it is easy to explain why this picture is showing a living room. The second method is local method, which helps to understand a single decision made over specific instances of a dataset. For example, Lime approximates a black box model locally in the neighborhood of any prediction of interest. The colored area corresponds to decision regions for a complex binary classification model. The black cross indicates the instance of interest. Dot corresponds to artificial data around the instance of interest. The dashed line represents a simple linear model fitted to the artificial data. The simple model explains local behaviors of the black box model around the instance of interest. Let's take the left-hand side picture as an example, which shows an ambiguous animal, half horse and half duck. The middle picture shows 100 superpixels identified for the picture. The right-hand side picture is artificial data which are created by using subsets of superpixels. Let's take the left-hand side picture as an example, which shows an ambiguous animal, half horse and half duck. The middle picture shows 100 superpixels identified for this figure. The right-hand side picture is artificial data which are created by using subset of superpixels. According to Lime, 1,000 probabilities are provided that the image belongs to one of the 1,000 classes used for training a network. It appears that the two most likely classes for the image are standard poodle with probability of 0.18 and goose with probability of 0.15. The last one is model-related methods, especially model-agnostic methods, which usually are used to explain artificial neural networks. This can be divided into four categories: visualization, knowledge extraction, influence method, and example-based explanation. Visualization always visualizes deep neural networks to explore the pattern hidden in a unit. For example, partial dependence plot (PDP) is a graphical representation that helps visualizing the average partial relationship between one or more input variables. The figure shows two one-way and one two-way partial dependence plots for the California housing dataset. The left plot in the figure shows the effect of the average occupancy on the median house price. We can clearly see a linear relationship when the average occupancy is inferior to 3%. Similarly, we could analyze the effect of the house age on the median house price in the middle plot. Individual conditional expectation extends partial dependence plot by revealing interactions and individual differences by disaggregating the PDP output. The figure below shows four ICE plots for the California housing dataset, where the corresponding partial dependence line, the orange line, overlay on the ICE lines, the blue lines. We could observe a linear relationship between the median income and the house price in the partial dependence line. However, the ICE lines show that there are some exceptions where the house price remains constant in some ranges of the median income. Another interesting example would be TensorFlow Playground, which is an interactive visualization of neural network. Knowledge extraction can represent the knowledge in the form of if-then rules learned by the model during training. For example, the figure shows a decision tree to identify two types of content pages, Talk 1 type and Talk 2 type. Such knowledge can also be learned from model distillation, where a small student model is trained to match a large pre-trained teacher model. Next, influence method estimates the importance or the relevance of a feature by changing the input or internal components and recording how much the changes affect model performance. For example, layer-wise relevance propagation scales to potentially highly complex deep neural networks. First, a standard forward pass through the model is performed, with which the network predicts. Then the model's output is backward propagated layer by layer following the neural pathways involved in the final decision by applying specific decomposition rules. The result is a heat map shown at the left bottom corner, indicating the contribution of individual input features to the prediction, so that we can know the network predict it is a rooster in the picture, mainly because of the red comb and the throttle. Example-based explanation shows the instance of the training dataset to explain the behavior of machine learning models. For example, Quick Draw from Google explains why a machine learning technique can or cannot recognize my drawing, which shows users the picture in a training set of the same class and of the similar classes. Except for machine learning, there are other several subfields in AI, such as robotics, expert system, fuzzy logic, natural language processing. Different AI systems can use different ways for explanation, and we are going to introduce them in general. A counterfactual explanation provides what-if information in terms of which alterations of the input features could change the output of a predictive model. For example, diverse counterfactual explanations. DICE is a novel model agnostic approach for generating counterfactual examples that are both actionable and diverse. Explanations in recommendation systems is a popular topic and has received considerable attention in recent years. Now let's see some real-world XAI projects. Academically, DARPA launched its XAI program in 2017 with the aim of developing new techniques capable of making intellectual systems explainable. Industrially, H2O driveless AI does explainable AI today with its machine learning interpretability model. This capability in H2O driveless AI employs a unique combination of techniques and methodologies such as LIME, Sharply, surrogate decision trees, partial dependence, and more. It uses an interactive dashboard to explain the results of both driverless AI model and external models. In summary, what kind of explanation do we need for AI systems? And what is a good explanation? Explanations should help users in understanding the model of the system in order to maintain it and to use it effectively. They should also assist the user when debugging the model to prevent and rectify incorrect conclusions. In addition, explanations can serve educational purposes and be helpful for people in discovering and understanding novel concepts in an application domain. Finally, explanations are related to users' trust and persuasion. They should convey a sense of actionability and convince users that the system's decisions are the most correct and convenient for them. Thank you for watching this video and enjoy AI.